We're going to continue to talk about Taylor polynomials and specifically about how we use them to approximate functions. So the words do matter. You need to know the difference between finding the number of terms, the order of the polynomial, or the highest degree in the polynomial. And all of those things can be very different. So for instance, here cosine of x equals this fourth degree polynomial is only showing the first three terms. So if it asks for the first three terms in a polynomial, it doesn't necessarily mean that it's going to be to the third degree. It very well could be, but more than likely it's not going to be. So be very careful with that. The order, we can have p sub 4 of x, and it might very well be, let's say y or f of x was the sine function. Well, remember the coefficient to that fourth degree term was 0. So p sub 4 for sine of x would look like x minus x cubed over 3 factorial, because the next term in that approximating polynomial built around 0 would be x to the 5th over 5 factorial. So that wouldn't be the fourth degree term. So here is the fourth order. That's the fourth order. That means how many derivatives we're going to find. It is to degree 3, and it only contains 2 terms. And so I'm slowing down, number one, because I sped through the last video on the previous lesson, and I probably really shouldn't have, but I figured 4 videos was enough for one lesson. I don't think anybody wanted to watch a 5th video. So order, degree, and number of terms means very different things. So make sure you pay attention to the words. The words matter. And a recent AP exam did require a student to know the difference between the order and the degree. So just pay attention to that. So suppose we wanted to find a fourth degree polynomial of the form p of x equals a naught, which is just like p naught, just the output of the function at that center point, and plus a sub 1 of x, where a sub 1 in this case would represent the first derivative at a, and then times x, and this would be centered at 0 specifically. A naught would be the output of the function at 0. A sub 2 would be the second derivative evaluated at 0, and it would contain that 2 factorial that we have to remember to put there, and then so on. So that's saying this is the form of the approximating polynomial. And I'm going to use the same function that I did on that last example that I sped through and slow down a little bit. We'll have some time here for you to actually see the work that's necessary. So we want the fourth degree polynomial. So we do want p sub 4, and we do need to show that fourth degree term. It doesn't say find the first 4 terms, which would be something completely different. Here's the first 4 terms. As you can clearly see, it would be a third degree. Be very careful again with that. So with our function, let me get rid of this work. Here's our function. I'll work over here. Our first derivative, 1 over x plus 1, and just like I did on the other lesson, I'm going to do that so I can use the chain rule. I do need the second derivative. I do need the third derivative. And I will, in this case, because of the way they've asked this, I will need this fourth derivative. I'm going to evaluate all of those at 0, my point of tangency. We'll get f of 0, which is 0, the natural log of 1 of 0. F prime at 0 is 1. F double prime at 0 is negative 1. This is negative 1 over 0 plus 1 squared. That's negative 1 over 1. The third derivative at 0 is 2 over 0 plus 1 cubed, or just 2. And the fourth derivative at 0 is negative 6 over 0 plus 1 to the fourth, or just negative 6. So the fourth degree, p sub 4 of x, would look like 0. Not going to write that down. Plus 1 times x minus a, where a is 0. So the very first term is just x. The second term is minus 1 over 2 factorial times x minus 0 squared. So that's what that would look like. The next one is plus 2x cubed over 3 factorial. And the next one is minus 6x to the 4th over 4 factorial. Now, that is perfectly good. Leave your work like that. This is the fourth degree Maclaurin polynomial for the function f of x equals natural log of the quantity x plus 1. However, if this was a multiple choice problem, it would look a little bit different. X minus x squared over 2 factorial, we can't do anything about that. But 3 factorial is 3 times 2. That's 6. And 4 factorial is 4 times 3 times 2. That's 24. So if this was a multiple choice question, you very easily could have your correct choice. The factorial would probably be dropped in this term, although it's still correct. This would reduce to plus x cubed over 3, and this would reduce to minus x to the 4th over 4. This is what your work would look like if it was a multiple choice problem, I can promise you. So sometimes those coefficients are going to clean up and reduce with your factorials. It probably is a good idea for you to just have in your head what for sure those factorials are. I might even say that one was negotiable. This is 24 times 5, that's 120. This is 120 times 6, that's 720. It probably wouldn't be a bad idea for you to have those factorials memorized. You probably don't have to do it really quickly, but over the course of what we're doing here in our series section, I think I would go ahead and memorize that. So here's what we're looking at. Here is p sub 4 of x, and I have it graphed in the plane with f of x. Near x equals 0, this becomes a really, really good approximation. As a matter of fact, almost to 1, and maybe almost to negative 1 over that whole interval right there, our polynomial mimics the behavior of our function in the plane really well. And you can see here that I have zoomed in so you can see even better that it's a really good approximation. Not very much error at all the further away from 0 we get. So we could use the polynomial to approximate the function very, very near the input values of 0, because that's where we built it. And so if we were asked to approximate the function at a given value, and usually that value is going to be close to the center point that we built around. Here we built around 0, and 1/4 is close to that. And so we're going to approximate f of 1/4 using our fourth degree Taylor polynomial. And then we want to know what is the difference in the two values. Well, p sub 4 at 1/4 means I'm going to plug 1/4 in everywhere there's an x. Because if this is p sub 4 of x, then here I can get p sub 4 of 1/4 by plugging in a 1/4 everywhere there's an x. Minus 1/4 to the 4th over 4. So we could do that by hand. We could find out what the difference in the two values were. We're going to have a little trouble without the help of a calculator, because this is what that value is if I plug in 1/4 there. And I don't, frankly, know what that is accurate to any decimal places. So let's get a decimal approximation for this and a decimal approximation for this, and we'll do a comparison. We'll find out what the difference in those two values are. Okay, so I put the function f of x into y1. So there's the function f of x, it's in y1. Hopefully you can see that. I don't know why it's not letting me write on it. And then I put our approximating polynomial into y2. And so you can see that it's fairly accurate. It's accurate if we round our polynomial. It's accurate to 3 decimal places. And so it wants to know the difference. Let's see, 0.223143. Let's write that down here, 0.223143. And then let's go back here, and we have 0.222981. 0.222981. And so we want to know the difference between those two. So let's see if it'll let me do it here. 0.223143 minus 0.222981. And the difference between them is 0. We move that decimal place 4 places to the left. So it's 0.00022. So the difference here, is 0.12322. This says we are accurate to 3 decimal places. We get to the 4th decimal place before we have any difference in those two values. That is pretty amazing. We have a 4th degree polynomial that 1/4 of a unit away from where we built it around, and there are infinitely many points between x equals 0 and x equals 1/4. All kinds of opportunities for this polynomial to stop acting like this function. But because we're in control of those derivatives and controlling the way the polynomial behaves, then we are assuring ourselves that the polynomial is going to be a good approximation for the function. So find the first 4 non-zero terms of the Taylor polynomial for f of x equals e to the x at x equal 2. This non-zero terms shows up a whole lot, because just like we saw a while ago, for the natural log of 1 plus x built around x equals 0, f of a, or f of 0, was the natural log of 1 plus 0, or 0. So that term is there. And so are we showing 0 or are we not showing 0 when we write p sub 4 like we did a while ago? Well, we didn't show it. And so it's not counted as a term. And so in order to take care of that ambiguity as to whether we should write 0 plus or not, they like to say show the first how many ever non-zero terms. So this is going to tell us that we're going to have to show the first 4 terms whose coefficients do not go to 0. So let's get started. I don't know that we'll get finished, but let's get started on how we're going to do this. So here's our function. F of x is e to the x. For the first 4 non-zero terms, I definitely need to go through the 3rd derivative. Now, if at any step, sorry, that should be the 2nd derivative. If at any step along the way one of those derivatives goes to 0, then I'm going to have to take another derivative. So you can kind of get started and say, okay, well, this is the minimum that I need, but if any of those go to 0, I'm going to have to add another term. If any of those go to 0, I'd have to add another term. So these derivatives are easy. E to the x is its own derivative. Not a problem. And then we need to evaluate all those at 2. I'll stop the video here and we'll pick up right here in the next video.